All right, so now the class is being recorded, and I'll post it probably this afternoon. I'll post a link or a file on the Blackboard website. All right. I guess the number is inaccurate. I don't think this is the 8th course. It's what? It's the 10th course, yeah. So this means we are behind the schedule by 2 courses, as far as I had made the schedule before. But that's fine, because I'm pretty much using the same material as last term, and this term is longer by a week. So this means that we are really not behind. Yeah. And again, I have postponed the midterm by 1 week. So let's see. All right, so the first topic is we're going to have another look at exact equations today. Namely, I wanted to tell you that an equation can be exact, or at least it can be made exact, even though it is not written in differential form. So on the second line here, we have an equation written in differential form: 4x cubed plus 2xy dx plus y squared plus x squared y dy is equal to 0. But this is equivalent to the equation written on the line above, at least as long as y squared plus x squared y is non-zero. So as you well know, you cannot divide by 0. So if y takes the value 0, then actually the form on the line above is less general than the form on the line below. Because if y is 0, then y squared plus x squared y is 0. But my other point is that you may see the equation in this form. So y squared plus x squared y, I mean, if the initial conditions make it non-zero, then this is a perfectly well-posed equation. And you cannot just tell by look at it whether it's exact or not. You have to test it. So would you like to see more about this topic? Well, in any case, I have one more example like this. So yeah. So if you look at this equation, I mean, I think even no matter how fast you are doing computations in your mind, it's hard to tell that it's really, let's see if this works, that it's really exact. So let's try to solve it on the whiteboard. Let's see, first of all, if I can copy it and paste. No, I cannot. So let's, so y prime is equal to minus 4x cubed plus 2xy over y squared plus x squared y. Yeah, so this equation, can you please tell me whether you can try to fit it into one of the types we have already studied, other than exact equations? So does it look like it's separable to you? Yeah, please. Well, it's not separable because there is no way you can factor either the denominator or the numerator in this fraction as a product of a function of x times a function of y. So at least I don't see any easy path towards making it separable. Is it linear? It's not linear because you see here we have y squared, for example. And also more importantly, because the fraction is nonlinear. So fraction, I mean, because we have y both in the denominator and in the numerator, and because they don't cancel or whatever, this fraction is nonlinear. It's a very nonlinear function of y. So it's not separable. Actually, let's use text here. So it's not separable. It's not linear. So by going down the list like this, we can find out whether the equation is of one of these types that we know how to solve or not. So this is the order in which I have presented them: separable, linear, exact. So the next check to do on the list is whether the equation is exact. I mean, the order in which you do it is up to you. And but in any case, exact is on the list, so we should check for it. So all right. So now let's test for exactness. So this equation as written is clearly not exact. So let's test that. So in order to make it exact, it's much more reasonable to multiply by the denominator of the fraction and then test whether it's exact or not. But let's test whether the equation is exact as written. So let's do it. So y prime is the same as dy over dx. So this equation is the same as, well, up to formally multiplying by dx. This equation is formally the same as dy is equal to minus 4x cubed plus 2xy over y squared plus x squared y times dx. And now if we bring everything to the same side, then we get, let's see, can I just, no, it doesn't check. Well, then I guess I'll have to copy it by hand. So 4x cubed plus 2xy over y squared plus x squared y dx plus dy is equal to 0. So if we do it in this unreasonable way, if we test this equation in this unreasonable way, then can you please tell me what is capital M and what is capital N in this equation? Nobody? Okay. So capital M is 4x cubed plus 2xy over y squared plus x squared y. And what is capital N? Can anybody tell me? Nobody again? Capital N is 1. So now we apply the exactness test. So we want to know whether partial m over partial y is equal to partial n over partial x. But partial m over partial y is whatever, and partial n over partial x is 0, and they're not equal. So partial m over partial y is equal to whatever. And partial n over partial x is 0. So one of them is 0, constantly 0. The other one is a function which is definitely not constantly 0, and they are not equal to each other. So as written, this equation is not exact. But it's pretty unreasonable to test it for exactness like that. So let's test the more reasonable version of it. Let's multiply the whole equation by this denominator, y squared plus x squared y. So what do we get? We get 4x cubed okay, this is good. 4x cubed plus 2xy dx plus what was there? X squared plus no, y squared plus x squared y dy so this is much more reasonable to test for exactness, and this is the test that you should do, not the one that I did on the previous page. So the original equation was not exact. We also tested that, but it can easily be made exact in a natural way. We don't know that it's exact yet at this stage, but at least you should perform this test when you see such an equation. So let's test it. So m here, so can anybody please tell me what m is here? Go ahead. Very good. So it's 4x cubed plus 2xy. And then, can you please tell me again?
Y squared plus x squared y.
Thanks. Y squared plus x squared y. Now, can you please tell me what's partial m over partial x?
X squared plus 2y.
Very good. Oh, but I applied the test wrong. Okay, you should have corrected me on that. So it's partial m over partial y. Let's see, did I write the test correctly on the previous page? Yeah, on the previous page I wrote it correctly. Partial m over partial y is equal to 2x. So let's see, the equation actually doesn't look like it's exact. Well, let's see, maybe the next one will be. So partial n over partial x let's see, I thought I had wanted this to be an example of an exact equation, but maybe we need to multiply it by something to make it exact. So let's also do that, even though that's not a required part of the curriculum. But I guess this may still be something that I wanted to show you, maybe. So this is 2xy here. So actually, turns out that even when I'm written like this equation is still not exact. So let's try to transform it again so that it becomes exact. And let's see. Yeah, I think we need to multiply the equation by y. Let's see. Let's make sure here. Did I copy the? Let's see. Let's modify the equation to make it exact because I don't care. So this is 4x cubed plus 2xy squared here. So we get 2xy. And now it's exact. And let's also do this on the previous page. And I'll make the appropriate modification in the lecture notes. All right, so next time I'll try to be more careful, but this time, whatever, I was in a hurry. So, okay, so now the equation is exact because I have made it exact. I mean, I have actually changed the equation. So these two things are equal. Oh, the test on the previous page still could not have made the equation exact because one of the things was 0 and the other one was non-zero. But now the equation written in this form is exact. So if we want, we can find the prime integral of this equation. Do you want to go ahead and find the prime integral of this equation or move on to the next example? Let's have a vote. Who wants to do this problem until the end? Who wants to move on to the next example? Right. So let's move on to the next example. So this is the next example. Let's write it on the board. To x sine y plus 3y dx plus x squared cosine y plus 3x plus y dy is equal to 0. So first, let's also write this equation using a fraction. And let's see that the two are almost equivalent. So this is equivalent to, well, except for at those points where the denominator cancels. So this is equivalent to what? Let's see, dy over dx is equal to what? Well, so it's equal to minus 2x sine y plus 3y over x squared cosine y plus 3x plus y. So again, there are some combinations of initial data for which the denominator is 0. And in that case, the two are not equivalent because you cannot divide by 0. On the other hand, if the denominator is not 0 for some initial data, then by continuity, the denominator will also be non-zero on some neighborhood of the initial data. And then we can divide by 0 by the denominator, not by 0, and solve the equation on some small neighborhood of those initial data. So it only matters whether the denominator is 0 at the starting point. If it is non-zero at the starting point, then there is some small region around it where the solution that we get will still have this denominator be non-zero, and then we can divide by the denominator and the two forms are equivalent. But can anybody please give me an example where the denominator actually is 0 other than the trivial example or x equal y equals 0? So do you know any other combination? Let's see. Actually, this is a good question even for myself. So I don't know what other value except for the pair x equal y equals 0 makes this denominator 0. But let's find out. So let's see. Okay, so one possible way to get non-trivial values is to set cosine y. So let's do a small set here. So if cosine y is 0, then so if cosine y is 0, then x squared cosine y will be 0, and then it's enough to set 3x plus y equals 0. So if cosine y is equal to 0 and x is equal to minus y over 3 is a good combination. So for example, we could have y is equal to pi over 2 and x is equal to minus pi over 6. So at such points, the denominator is 0. And so the thing that I wanted to say is that at these points, like this example here, the equation above, so the one written in differential form, is still perfectly valid, is still perfectly well posed, but the equation below is not valid, is not well posed because we are dividing by 0. So the two forms are not perfectly equivalent, even though they are mostly equivalent. Okay. All right. So now let's take this equation and solve it as an example. So let's start with the differential form already. All right, so let's go through this again. Can you please tell me what is capital M? You who answered earlier, sorry. By the way, what's your name? What's your name? Ben. So sorry, Ben, can you please tell me again what capital M and capital N are?
Yeah, M is 2x sine y plus 3y. 2x is 2x sine y. 3y is 2x cosine y. 3y is 2x sine y. 3y is 2x cosine y. 3y is 2x sine y. 3y is 2x cosine y. 3y is 2x cosine y. 3y is 2x sine y. 3y is 2x cosine 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 y. 3y is 2
and n.
X squared plus y plus 3x.
So now, what is partial m over partial y?
2x plus y plus
And partial n over partial x.
2x plus y plus 3.
That's right. So in both of these cases, well, I mean, I knew that example would turn out to be exact, but it's good to actually compute them and check. So yeah, so the derivative of x squared cosine y is 2x cosine y, because we treat cosine y as a constant. Derivative of 3x is 3, and the derivative of y is 0 because we are taking partial derivatives with respect to x, and partial y over partial x is 0. So here, when solving these types, this type of problem and similar problems, we don't take x to be a function of y or y to be as a function of x. When doing this test and in related computations, we treat x and y as independent variables. So at this stage, we are not assuming that y is a function of x or x is a function of y. So partial y over partial x will be 0, and partial x over partial y will also be 0 in this computation. So this is, again, 2x cosine y. So this is the same as when we did the next thing. So now let's use that method to find the prime integral. So there as well, we do not treat x as a function of y or y as a function of x, but we treat them as independent variables. So now we need to solve this system, no, the other system. So we want to find a function capital F, the prime integral, such that partial f over partial x is equal to capital M. And partial f over partial y is equal to capital N. So let's copy them. 2x sine y plus 3y. Hi, everyone, again. So 2x sine y plus 3y. And capital N is x squared. No, let's check again. X squared cosine y plus 3x plus y. Yeah, sure. Okay, so now let's solve the two equations one at a time. So f is equal to the integral of 2x sine y plus 3y dx. So now I repeat the observation made on the previous page. When computing this integral, just like when doing that test, we are not assuming that x is a function of y or y is a function of x. Or in this context, we treat them as independent variables. So in this case, we know what the integral of y dx is. It's y times x. So, but I mean, of course, I have shown this to you before, but now I wanted to emphasize certain things. So can you please tell me what is the whole integral? Ben, again?
X squared sine y plus 3y.
Thanks. So yeah, let's erase the integral sign here. So it's x squared y, x squared sine y, I meant. Plus 3xy. And then the antiderivative, as I have said, is only unique up to a constant. And in this case, for each individual value of y, we get a different constant. So this constant is actually a function of y, which let's denote by c of y. And now we want to match this with the second equation. So let's compute partial f over partial y using this partial answer. So this is a correct answer, but it's only a partial answer because we don't know what c of y is yet. So let's compare with the second equation and discover what c of y has to be. So partial f over partial y is equal to, so now we're using the second expression here. So Ben, can you please tell me again what partial f over partial y is?
X squared plus y plus 3x.
Yeah, plus c prime of y. Okay, so now we see that the two expressions are almost exactly the same, except that one of them contains a y here, the other one contains c prime of y. So what this means is that in order to solve this equation, we must set c prime of y equal to y. So Ben, can you please tell me again what C is under these conditions? Okay, so C of y, by taking the antiderivative of y, we get that it is y squared over 2 plus a constant. So the reason why this is an actual constant and not a function of x is because C, if you look at the previous page, is only a function of y. So we already got rid of the x dependence at this stage. It's only an ordinary differential equation, exactly as it looks. So for f, we had a pair of partial differential equations. So this is a system of two partial differential equations. But for C here, this is why I wrote C prime instead of partial C over partial y, to emphasize that it's only a function of y, and this is an ordinary derivative here. So then we can solve it in this very, very straightforward manner, which I think I pointed out to you in the first course. This was one of the first kinds of ordinary differential equations that I mentioned to you. And I said that it's very simple and straightforward to solve. And let's call this constant C1 to distinguish it from C, which is a function of y here. So all right, so we have almost solved this problem. We get that f of x and y. So f is a function of two variables. C is only a function of one variable, namely y. So, okay, I have one more point to make here. If everything did not cancel so properly, if we did not end up with C prime of y being just a function of y, like I said, this would mean that the equation is not exact. So, but we already knew that it's exact because we tested it. So the fact that after cancellations here, we get that C prime of y is only a function of y and not of x is because this equation is exact. This can be considered a second test. So the first test is when you set partial m over partial y equal to partial n over partial x. Are they equal or not? The second test, which you can do, is if C prime of y, after you cancel everything on both sides, if C prime of y remains equal to only a function of y. If after cancellations you have got something like, for example, C prime of y is equal to y plus x squared, then this means that there was an error up to that point, and you have to go back and fix it. So it actually probably means that the equation was not exact to begin with. But in this case, everything worked out. So C prime of y is just a function of y. So the second test confirms the first test. And then, so let's write f of x and y completely. So it's x squared sine y plus 3xy plus y squared over 2. That's again, so x squared sine y plus 3xy plus y squared over 2 plus C1. So again, recall that prime integrals are kind of antiderivative, so they're only unique up to a constant. So this is the general form of the prime integral that we are getting here. So you don't actually need to do the second test that I just mentioned. One test is enough. But the second test checks whether the first test was done correctly. That's all. So the general solution of the equation is, in implicit form, the general solution of the equation is x squared sine y, right here, implicit. Okay, so in implicit form, the solution is x squared sine y Where did the text go? Oh, maybe it's okay. Let's do the text better. So the implicit solution is x squared sine y plus 3xy plus y squared over 2 is equal to C2, where C2 is another constant, not necessarily the same as C1. And since this is a quadratic equation in x, we could solve it for x as a function of y. It's much harder to solve for y as a function of x because of the sine y. So the solution cannot be given by elementary functions. Maybe there exists some special function to solve it, but I have no actual idea. So, I mean, I think that there's no point in even trying. But we can solve it for x as a function of y. So what do we get? So let's see. So let's write here explicit solution. So let's write x is a function of y. All right, so then again, can you please tell me what's the solution of this quadratic equation? So x of y is equal to, or does anybody else want to solve this quadratic equation? Let's go. What? No, this is a quadratic equation. You need to solve it using the quadratic formula. Anybody else wants to try? Ben again? Okay, so solution of the quadratic equation is minus b plus or minus square root of b squared minus 4ac, everything divided by 2a. So this is minus 3x plus or minus square root of So b is 3x here. Actually, let's write this. So 3x here, let's circle it, and this is b. So b squared is 9x squared now. Minus 4, and a is x squared here. So it's 4x squared. And can anybody please tell me what c is in this equation? If you have been paying attention. Ben? No, what is c? So remember that we are solving for x. So you should have said y squared over 2. But that's not the actual answer. So what is c? Anybody? So you know that in the standard formula for solving the quadratic equation, all the terms are on the same side, and you set it equal to 0. So if you put all the terms on the same side, then what would c be? It would be y squared over 2 minus c2. So you need to pay attention to this when solving a quadratic equation. In order to use the standard formula, you first need to put all the terms on the same side and identify what a, b, and c are correctly. Because it is very possible to do mistakes with this step, even with this step. So c here is equal to y squared over 2 minus c2. So that's what, and here, oops, so here I guess I misidentified the coefficient here, so that's fine. Let's erase it and, okay, so the coefficient here is sine y. Coefficient here, so let's erase this too. Coefficient here is of x is 3 times y, so let's erase it and make it correct. So b is 3 times y. So a is sine y. B is 3 times y, and c is y squared over 2 minus c2. So then let's make this also correct. Right, and here inside it's 9y squared minus 4 times sine y, so 4a, so that's sine y, times y squared over 2 minus c2. And it's everything divided by (2a), 2 sine y. Okay, so sorry for going over time. I didn't even know where time has gone. Okay, I didn't even notice until now that we are much over time. So thanks for your attention. Well, actually, you're only over time by 5 minutes. Maybe that's not so much. So thanks again for your attention. If you want, we can continue this next time, but we're probably just going to move on to Bernoulli type equations. Yeah, but I think that it's important to see these kinds of examples. I think that this should be good preparation for the exam. All right, thanks again.